So, hello everyone, welcome to the course on architectural design of ICs. So, we are basically considering the timing analysis basics, whether that is static timing analysis or dynamic timing analysis. So, they are very much important whenever we are considering any digital circuit design or digital integrated circuit design. So, in static timing analysis, we have already seen that okay, there may be more than one path, or there may be, that means many paths. So, from input to the output, which path is basically considering the maximum number of delay. So, that is the cycle time requirement of your circuit design. Okay. So, the delay of a single path that can be calculated based on the intrinsic gate delay plus this fan out delay plus the wear delay. So, this intrinsic delay, okay. So, the intrinsic delay means the inherent delay which corresponds to the each of the gates, okay. And if one of this particular inverter is now driving 4 different other cells, so at that time their delay will be, information will be this fan out delay. If it drives 2 delay, that means 2 gates here. So, at that time what will be the amount of delay for these gates. If it is driving more than, that means if it is that means 6 cells here. So, at that time delay will be more for this particular cells, as well as this corresponds, actually there are 4, that means paths it is driving, means that there are 4 paths, that is 4 wires which is connected from this particular edge. So, the wear delay will be also considered in the corresponding path delay or the combinatorial circuit delay. So, this, as this fan out is 4. So, the gate fan out delay is caused by the input capacitance of the gates in the fan out cells. Okay. And then how this gate fan out cells, basically this gate fan out delay is calculated based on the capacitive load of the CMOS inputs which it is driving. Okay. So, depending on this R and C value, we can calculate that how much delay it corresponds to that, what is the number of fan out for this particular gate. Okay. So, depending on that we can calculate or we can compute, or in static timing analysis tool this is being computed. So, if one gate, actually how we can compute is that this approximated by the factor n, which is the fan out, and then the delay, that means d is the delay amount for per fan out. Okay. So, if as an example, if we consider that one gate has 0.5 nanosecond delay per fan out. So, when it is driving 3 gates will cost 1.5 nanoseconds of delay. So, this information will be basically stored, or this information will be changed depending on different library. Okay. So, then in total, actually if we calculate the total path delay of any circuit, which corresponds to the 2 nanosecond delay over here, and then actually if that is also 1. So, the intrinsic, the path delay, or this actually the fan out delay, if one of the fan out delay is, let us say 0.5 nanoseconds. So, for 4 it will be of 2 nanoseconds delay. Okay. So, the path it is showing is that the one is the corresponding, this one is this the delay for this particular gate, and then 2 is for this fan out delay, and this wear delay, let us say that is of 1. So, the total path consists of 4 nanoseconds of delay. So, after placement and routing has completed, additional correction factors can be included, which is the delay of wears. So, now STA, that means STA is nothing but the static timing analysis. They may find paths which are never activated during operations. So, such paths are called as false paths. So, what is that means example of false path is that suppose we are having two paths, that means two logic, here this is the combinational logic, here we are having 1 and 0, and again we are having this combinational path logic which is having this 1 and 0. So, whenever this select equals to this select, let us say this select equals to 1. So, at that time particularly this particular path, whenever this is 1 means this is 0. So, the corresponding logic will pass from this to this. Okay. So, the STMA finds that there are never one activated path during the operations, and such of those paths are called as false path, and the designer must indicate such false paths to the STA tools so that it does not actually calculates or it does not include the timing information of those false paths. Otherwise, what will happen is the timing information will be misled to the some other values. Okay. So, even though the red path has the longest delay, it will never be triggered in practice because this is a false path. Okay. So, the timing constant are basically additionally directives provided by the designers to the synthesis tool, and these timing constants are used by the static timing analysis to verify if the timing of the resulting circuit is okay. That means, in terms of this clock period requirement, in terms of this setup time or this hold time violations are there or not. Okay. So, after this place and route, this timing constant also be used to the place and route tools to decide how the components should be placed into a corresponding the chip area within the chip area. Why? As we have already said that this clock skew or this delay amount, they are basically calculated based on the how they are connected to each of them to another one. Okay. So, then we have already known that okay, what is the slack? Slack is the required time minus the actual arrival time. Okay. So, if we cascade these two flip flops in, that means in series. So, at that time suppose this clock is connected to this and this Q0 and the Q1 flip flop. So, this is the input which is again going to the that means the second the registers. So, if we see that okay, this is the input signals, this is the variation in the input signals, and this Q0 is basically is this one, and then the Q1 will be depending on the clock edge. Okay. So, this Q0 value is 0, sorry, this in is, that means in is 1. So, that means after some times the Q0 value will be 1, which is this the amount of t, that means the time which is going from t high to low or the low to high. Okay. So, the t, this setup plus the t requirement for this particular flip flop or the delay of the flip flop, that is the minimum requirement of the t cycle over here in this particular circuit design. Okay. So, whenever we are cascading two flip flop, so at that time this the propagation delays, if it exceeds the hold time, at that time the second stage commits its input before the Q0 changes. Okay. So, for that particular things we have to consider the system like how we can correct, or there are some basic rules to correct the timing, is that whenever the two flip flops are synchronously connected to, that means their operation or they are operating at the same event of the clock. So, no flip flop changes the state more than once per clock cycles. or the flip-flop propagation delay should be more than the hold time. And always avoid the mixing of this positive edge triggered and the negative edge triggered flip flops in the same circuit. So, again when we use edge triggered flip flops, whenever it is possible, always try to avoid the latches, and most commonly used of the, that means this edge triggered flip flop is the master slave configuration of the D flip flop. Okay. So, the clock skew is, we have already discussed. So, that means if there is the, depending on the arrival of the clock, if there is a time gap between the clock edge. So, at that time how much is the time gap, that is the clock skew. So, this, the calculation of the clock skew we have already said, and then actually what is the difference of the synchronous circuit and the asynchronous circuit. So, the in asynchronous circuit, the state changes occurs when the state input changes, and the feedback elements may be waves or delays. But in synchronous circuit, the state change occurs synchronously and the feedback elements are clocked. That means what? In asynchronous circuit, we may have different clock which has been different event or the triggering point at different time instant, but in synchronous circuit all that means event occurs at the same timing instant. So, that every, that means every this sequential element, they can fire or they can that means start their working at the same instant. Okay. So, when actually this asynchronous input means to deal with this asynchronous circuit, that is much more critical to work with the synchronous circuit. So, when these clock circuits are synchronous, the circuit changes its state only at the clock edge, whether that may be positive edge or whether that may be at the negative edge, and the signals settle in between the clock edges only. In unclocked circuits, or the signals are asynchronous. So, no master clock, the real world inputs are asynchronous, like this key pressing, all these real world inputs are asynchronous. So, whenever we are dealing with this asynchronous inputs, so at that time these synchronous circuits may have this asynchronous inputs like this reset signals, memory wait, user inputs, etc. The input can change at any time, so that we must synchronize the input to our clock or with our clock, and inputs will violate the flip flop setup and hold times. Okay. So, which causes this synchronizer failure? So, when it occurs when the flip flop input changes near to the clock edge. So, what will happen at that time, the input is neither 1 or 0 when the clock goes high. The output may be neither 0 or 1, they may actually they may stand undefined, it may also known as this metastable state or unambiguous state it can reach to. So, that you cannot recognize the data properly, that whether it is in 0 state or whether it is in 1 state, which causes this synchronization failure. Okay. So, if we see that what causes this synchronization failure is that, suppose this is the clock edge, and at this particular clock edge if the data changes its value. So, at that time it does not recognize that whether that values is 0 or it will pass the values of 1. So, that is named as synchronization failure. So, how to minimize this synchronization failure is that so, failure probability can never be 0. So, cascade 2 flip flops, effectively synchronization use is twice, and both would have to fail for system to fail. When both of them are failed, so at that time only the systems will be failed. Okay. So, why this? Suppose this input is coming from this asynchronous that means asynchronously. So, at that time this first D flip flop will be, depending on the clock, it will pass to this, and then again whatever will be that means because of this asynchronous input, whatever changes it occurs here, it will first, that will be mitigated through this second D flop what we used here. So, the in while we are doing this clock domain crossing, so at that time we use this kind of synchronizer circuit to minimize this synchronization failure, where as we have already said that the real world inputs are mostly asynchronous in nature. So, after actually whenever we are giving the signals to the, that means our IC, that means designed IC. So, at that time it should be passed through a synchronizer, so that the inputs, all the inputs, so the inputs may be different at different times. So, they may be multi-bit. So, all the inputs are basically synchronized and it goes to the system, or it goes to the corresponding that means IC at the same time, or depending on the same event. Okay. So, how to handle the asynchronous inputs is that this never this fan out asynchronous inputs synchronize at the circuit's boundary and then fan out this synchronized signals. So, means what? Suppose we are having two D flip flops and here we are this asynchronous circuit, in that means these inputs are coming, asynchronous inputs are coming. So, if we do, that means if we connect, that means here directly, then again it is coming with one another, that means this path is longer than this one. So, at that time, at the very boundary of itself, we need to put this synchronizer. Okay. So, that means this path is also becoming one clock dependent, that means, and then again from here to again it is connected to the next flip flop, which is the second flip flop. Now, depending on that, it will be just work as a synchronizer circuit, which will be. So, clock domain crossing means, suppose this is 1 volt, one of the, that means this depends on the sample clock, and then we are having this design clock, or this integrated circuits clock, which is the system clock. Okay. So, depending on this system clock, we are now putting this extra D flip flop over here to the inputs, we are making synchronized with the full system clock, though their inputs are asynchronous in nature. Okay. So, thank you for today.